Okay, so good morning, everyone. So we'll start from where we ended yesterday. So recall that we had this yesterday we stated two generic theorems for convergence rates of posterior distributions. And we ended with this second result, saying that if you have enough prior mass, so that was the same condition as in the first result, as well as the sieve one. And it was only in the first result we had the testing condition. We had to test a point against the complement of a ball. And maybe that's not super easy. Okay, so you have to test point against complement. So we said that actually it's perhaps easier to have just a condition of testing points against ball and then adding an entropy condition. Okay, and now I'll explain briefly why indeed you can deduce this second result from the first of last time. So that's just a little lemma that essentially says exactly this. So if we have t, so I will not rewrite t, but okay, it's just that you can test with exponential power to a point versus a ball. Okay, so you have 2 points distant of at least epsilon, and here you have a ball of radius slightly smaller than epsilon, s smaller than 1, and here t says that you can build a test such that its first kind error is exponentially bounded in epsilon, as well as the second type error. Okay, so that's the point versus ball testing condition. Okay, for a distance d. Okay, and suppose that the entropy, so the logarithm of the minimal number of balls necessary to cover the sieve set theta n by balls of radius epsilon n for the distance d is smaller than d n epsilon n squared. Then for a given c, there exists an m which depends on a, k, c. So k is the constant in the exponential decrease. A is this, which is smaller than 1, and c is this constant that we have here, and tests psi n, okay, such that the first condition, so the testing condition, condition 1 of the first GGV theorem is satisfied. Okay. So this is exactly it's more or less what you need to prove this. So more or less the only difference is that here I introduced, as I said, for more flexibility, two rates. And the final rate here, epsilon n, I didn't rewrite it, is the minimum of, is the maximum of the two. So this is just so that one is not, so you can check independently these two conditions and this first. Okay? So before, I'll just give the idea of proof. I will, so it's in the notes here. So what's the idea to prove that? So you want to build this test psi n. So remember, it's point against complement of a ball. So what you do is that you use what's called sometimes peeling argument. So you cover the complement of the ball by some shells like this. Okay. And each shell you cover it by balls. Okay. And for each one of these balls, you have a test now by the condition t. Okay, so here you have some centers, I don't know, theta ij. Here, for which I have a certain test phi ij, okay, with the exponential decrease of the errors. And you do that for any shell and any interior of the shell, okay? So here I have some shells, C1, C2, etc. Okay, and at the end I just do, I just set psi n to be the sup over, so say J is the index for the shells of the max over I, because each shell has a finite number of covering points of the test phi ij. Okay, and since there is this exponential decrease, okay, so I can write it here. E theta naught is smaller than E minus K n epsilon squared, and then you have, for the alternative, you have that the sup over the ball, theta in the ball, of E theta 1 minus phi n is again smaller than E minus K n epsilon squared. Okay, and because of this exponential decrease, you can sum up the different errors, and this psi n exactly verifies condition 1 of the first GGV theorem. Okay, so that's just the sketch, the idea of. And so if you want to have all the details, it's in the notes. Okay, and so now, to wrap up, the question is, okay, are there many distances for which you can verify the condition T? Okay, so what are distances D that work? Well, that depends on the problem, but generally there are natural distances for many problems that will work. So, because point versus ball is really the simplest thing, almost the simplest thing you can think of. The simplest would be just 2 points, but so you can use often like likelihood ratio tests or things like this. So in density estimation, for instance, there always are tests that verify these T conditions when D is either the L1 distance or the Hellinger distance. Okay, so the Hellinger is just squared, is just the L2 distance between the square roots of densities. Okay, and in Gaussian regression models, as we saw last time, you can typically take an L2 distance, so either a continuous L2 or discrete L2 distance. For instance, for the Gaussian sequence model, you can take the little L2 distance. Okay, and so that's just a little exercise each time. So for instance, here in density estimation, it's just the use of Hoeffding's inequality. So I think I put that in the appendix in the notes, just checking these conditions for the classical models I gave. And in very many models, as soon as, for instance, you have independence, you can take D, a type of Hellinger distance often. So it's fairly broad. Okay. But there are distances for which actually it's harder, and we don't know how to verify this. And I'll come back to this a bit later in the course. Okay, so I think if you have questions now, maybe it's a good point to, yes?
Could you explain again what is the A constant here?
The A constant is just so you take 2 points that are separated by at least epsilon. And so, of course, you just don't want the ball to intersect theta naught, because otherwise you cannot test. So it is just to make sure that this ball doesn't touch the point, doesn't intersect the point theta naught, doesn't contain theta naught. Okay. So
any constant level 1?
Yes. Okay. So, but it's an assumption. So you need to be able to find a constant A a universal constant A such that for any pair of points theta naught, theta 1, okay? But in general, in most settings, you can just take A equals a half, for instance, or it's not very important. Sure. Thanks. Okay. Other questions? Okay, so now what we have at our disposal are two generic, or say if we look at this one, a generic result to get a convergence rate of a posterior distribution, and with some qualitative conditions that one can check for, in principle, any prior you like. Okay, so and now in this second lecture we'll start looking at examples of various priors. In particular, we'll look at random histograms and Gaussian process priors. But before that, I'll just discuss a few extensions or a few related results regarding this generic theorem. So one thing that I can say while I'm erasing is that there are many variants of these results. You have many refinements. So for instance, as you may recall from the proof of yesterday, in the proof we kind of separate the numerator and the denominator. Okay, so we treat separately the denominator. We bound it from below, and then separately, once we have done that, we deal with the numerator. Okay, and in particular here, we take a bound uniform in theta. So here there is no theta naught showing up here in the prior mass condition, and that can be a problem if for unbounded parameter sets, of course. So if theta naught goes very far away, goes to infinity, of course, at some point you'll have no prior mass, so you cannot verify a condition like this. And typically, so if you have unbounded sets, you'll have some theta naught showing up also there, if theta naught is allowed to go to infinity. And then if you want to be able to deal with those situations without imposing boundedness conditions, you need to be a bit more careful and treat numerator and denominator together. Okay, so that's a bit more technical, but I'll come to that a bit later, give a little example of that. There are many, also you can refine, you can take other type of entropies here, like local entropies. Okay, so, all right, so far we have, so here what you can keep in mind is that for regression models, this theorem will give you already many results for D equal to an L2 type distance. And if you are in density estimation, maybe more for an L1 or Hellinger distance. Okay, so before we look at some classes of examples, I'd like to talk about something that's quite popular, in particular in the machine learning literature, and what's called the fractional or tempered posteriors. Okay, so what's that? So it's you start from base formula, but instead of taking the likelihood, so you have this ratio formula, okay, for the conditional that we wrote yesterday. Okay, integral over B. So here I look at the posterior mass of a set B. Okay, divided by the normalizing constant. Okay, so here the fractional posterior is just, you take this as a definition, but you put a power alpha here. Okay, so what's the interpretation of this is that depending on the alpha, you give more or less importance to the data relative to the prior. Okay, so if you imagine that, so if you put alpha equals to 0, then what you get is just, you just get the prior. Okay, so pi is just pi, so there is no influence at all of the data. Okay, so if alpha is equal to 1, you get the usual posterior. Okay, and there is also a regime where alpha is larger than 1. So if you imagine that you let tend alpha to infinity, so then what you will get is that, so if you have a power that is very large here, the values that become important in these integrals are only those for which this is close to the maximum. So you get something that is close to, so I'll put some guillemets here. You get maximum likelihood in a sense. Okay, so and then there is no prior anymore. Okay, so this kind of interpolates between these two extreme situations, and the situation we'll be interested in here is alpha between 0 and 1. Okay, where you slightly downweight the data. Okay, and so the question is, can we get a convergence rate for this? And quite surprisingly, perhaps you actually, so you have a result similar to this, but where you can erase the first two in a sense. So that's kind of neat. So let's write that. So I'll need a distance. The alpha Rényi, it's a classical divergence, sorry, distance, alpha Rényi divergence between two probability measure P and Q of order alpha. It is just, so alpha, the alpha PQ is minus, so it's equal to minus 1 over 1 minus alpha, the log of integral. So here I'll assume that, so let's just take for convenience a dominating measure mu and densities q, small p and small q. And this is p to the alpha, q to the 1 minus alpha d mu. Okay. So that will appear naturally in the next result. So theorem 2.1, I think. So we take epsilon n such that n alpha epsilon n squared goes to infinity. And we assume that, again, the Kullback-Leibler ball of radius epsilon n around theta naught has probability, prior probability bounded from below by n alpha, by an exponential term. So you need at least this amount of mass. Then there exists a constant c independent of alpha, such that this converges, you get, so p pi of, so I need to be a bit careful with normalization, d alpha of p theta naught. So recall that, so I don't put the n here, but you can put the n. Okay, so that's why here you get a normalization. Is larger than some quantity. Okay, that will, in a moment, we'll see that this alpha will actually cancel typically left and right. Given x is little op theta naught of 1. Okay, so when I write little op, I could actually just write as before, maybe, to be consistent with what I wrote before. Is a little o of 1, or goes to 0 as n goes to infinity. Okay? All right, so that's interesting. So here, note that I inserted alpha here, and the constant is independent of alpha. So here it's allowed. I can actually take alpha equals alpha n goes to 0 in this result. Okay. So before giving the proof, let's just maybe interpret that a little bit. How can we say something a bit more? Maybe transfer this alpha Rényi divergence into other distances for simpler models, for simple models, just to interpret a little bit. Because here we have dependency in alpha here. This still depends on both alpha and n. Okay. So I'll just take the case of product measures. So p theta equal to q theta tensor n, okay, and then we have a classic. So this just tensorizes. So d alpha p theta naught is just n times d alpha q theta naught. And this is larger, so there is something called Pinsker's inequality, which relates the alpha Rényi divergence to the L1 distance. So this is larger, the n is still there, and then times alpha q theta minus q theta naught L1. Okay, so if we put everything together, you see that actually we get rate. So in terms of the L1 distance, so for the L1 distance, which is, so if you simplify the n alpha, the n goes, and also the alpha goes, so you get the rate c epsilon n squared divided by 1 minus alpha. Okay, for in terms of L1. So if alpha is bounded away from 1, so if alpha is a half, for instance, you get a constant times epsilon n squared. Okay? So for the squared, sorry, there is a square missing here, for the square L1 distance. Okay, so that's nice. So what can we say more? So why is it natural to have this 1 minus alpha? So note that if alpha goes to 1, in principle this blows up. Okay, and in fact it's related to the fact that here these conditions in a sense are really needed. So there are examples where you can show that if you don't have these conditions, only under prior mass condition the posterior can fail to converge. Okay, but it turns out that for the tempered posterior, this cannot happen thanks to this result. But this 1 minus alpha here at the denominator reflects that things may go wrong to when alpha goes to 1. Okay, but I would say that it's not completely understood exactly when this happened. So there are examples where you can show that both will be fine, even though you are not able to verify this. Okay, so let's give. Yes.
A very precise question. So you make the proof in the case of product measures, and also in the statement in your notes, you use some notation with p theta 0 to the power of n without
yes.
parentheses, which at some point you said it's only for product measures. So what is the level of generality of this theorem?
So this theorem is valid for so when I put the n here is general, so in parentheses. So this theorem is for under the generic framework of yesterday, so it doesn't have to be a product measure. And it's just that here for the interpretation, I should say special case of product measure, just to ease the interpretation of this, I gave this little example. Okay, right? Yeah, thanks. Okay, great. So we'll see that the proof is actually very. It's essentially the same as what we had yesterday. So I'll not redo. So I'll just say, so for the denominator, we bound it almost in the same way. And so maybe waiting that it dries a bit. So this version is actually from a recent work we did with Alice here and Colin Ray and Luke Travis in London. And so we were interested in understanding the dependency in alpha in such results. And from this result, you can actually show that, so if, say, for alpha equals 1, you get the rate n to the minus gamma. So when alpha is between 0 and 1, from this result in many situations, so I don't have time to go in details, but you can already see here that you have this n alpha that you could call n prime. Okay, so here, this n prime is the rate you actually get for the alpha posterior. So for the tempered posterior, in a sense, you get the same rate, but with a different effective data number, which is n prime equals to alpha n. In a sense, it makes sense given that you kind of downweight the number of data by alpha. Okay, so this is in special situations, again, in like product measures and things like this. But we're just to give a bit of intuition. Yes?
I have a question, because you seem to alternate between this interpretation of the alpha posterior as if there was another like Bayesian method.
No, yeah, good point. No.
But here it's just like you have the same posterior as usual, but you just look at the specific distance between measures.
No. So here, sorry. So here it's the alpha posterior. Sorry.
Oh, okay.
Sorry. Thanks. Of course. Yeah, forgot that. So that's a result for the alpha posterior. Yeah. Thanks a lot. Yeah. Sure.
So the conditioning you're looking at is the Bayes formula.
So sure. So this is actually this is an abuse of notation. So actually, I should. Yeah, you're right. Absolutely. I should rather. I don't know. I should call it. So this is a measure. And I should just call it pi tilde x if you want, but it's not. So you're absolutely right. Thanks. I forgot to say that. You lose the Bayesian interpretation as a conditional distribution, and in particular, you may lose some optimality properties of related to the use of the likelihood, and I'll comment on that a bit later in the notes in the lectures. Yeah, thanks a lot. Yeah, sure. It's for pi alpha here. Yeah, I forgot to say that. So I wrote it as if it was a conditional, but in fact it's not. Yeah, sure. You're right.
And can you come back to a Bayesian interpretation if the densities p theta to the alpha are actually densities? I mean, if you can normalize everything so that it's integrable. I don't know.
I'm not sure, because then it depends on the theta. So so for me, it's just a measure that depends, a probability measure that depends on the data that I gave this definition. But yeah.
No.
So don't we want alpha going to 1, because then that statement would be similar to this one?
Yes, so that's, yeah, indeed. So that's what I said. So indeed, it's very tempting to let alpha go to 1, but the problem is that, so this blows up, okay? So it suggests that, so then we cannot do that, right? So but this is kind of natural, this is a bit expected because you have these extra conditions. So maybe, but as I said, it's not completely, so those are only upper bounds. So it is okay, so, thanks. Okay, so let's do, let's check, do a sketch of proof quickly. So it's really the same. So yeah, sorry. Maybe I should actually write it rather like this, depending on x. So this is for some set A that I'm going to choose in a second. So I'll do the same trick as yesterday. I divide by p theta naught. Now I have this powers alpha. Okay, so the denominator now is really the same as yesterday. So it's a certain d. Maybe I should call it delta because I have a d there. A delta alpha, and it is going to be larger than e to the minus, so just have to be a bit careful with the alpha, times pi of b. Okay, so that's on event, so with probability at least something that goes to 1, right? So C, and epsilon squared. Okay, and once I have this, so I can take the expectation and the theta naught, and I do Fubini like yesterday. So here, so that's smaller than, so e to the 2n, so alpha phi of b, so this like yesterday could be. And here I get integral over a, I do Fubini, so I get the integral p theta alpha, p theta naught 1 minus alpha of little x d mu of x. Okay, and I integrate over pi. So now let's choose alpha such that, so here it really looks like so I just erase the definition, but it looks a little bit like the Rayleigh up to the log. So let's introduce the set. So let A be the set of thetas for which this is nice. So suppose this is just smaller than some exponential term. E to the minus, say, 4n alpha epsilon n squared. Okay. Well, then, if you set this, so it just turns out that if you just take the log and 1 minus 1 over 1 minus alpha, the log, then you get exactly the Rayleigh. Smaller than 4, so I divide also by, yes, so I can leave the n to the right hand side, 4n alpha epsilon n squared. Okay, and so this is the d alpha p theta 0. Okay, so that's the one we got there, and so we divide by n, and then we get so that's the okay. So then I have to divide also by 1 minus alpha here. Okay, and so that's and dividing by n, I just get actually that this is the set I'm considering in the theorem. All right, but for this set, then this here is bounded by this exponential quantity. So therefore, I can just conclude the proof over here. This is smaller than, if I add up all the square here. So it's e to the 3n alpha epsilon n squared, because I get 1 from here, pi b, from this condition. Okay. And e to the minus 4n alpha epsilon n squared. Okay, so that goes to 0. Okay, so that's conclusive. Okay, so we have this extra tool at our disposal saying that maybe in situations where it's complicated to verify this, we can take maybe the alpha posterior, and maybe if alpha is a half or if alpha is 0.9, maybe it's not that different from the original posterior. So I'll come back a bit to that later on. All right, so now we can set to families of examples and see how we can apply these generic results. So the first family of examples we'll consider is just simplest possible functions, random functions, in a sense, is random histograms, just to warm up. and then we'll move to Gaussian processes, which will be like a building block for more complicated priors later on. Okay, and so we'll just for random histograms and for GPs for Gaussian processes, we'll just see how to check this. Okay, so first nonparametric example. So random histograms, random histogram priors. Okay, so I'll just do, so the model will be very simple. I'll just take Gaussian white noise on 0, 1. So the reason I do this, I say again, is that since it's in continuous time, I don't need to worry about discretization. So we could do also nonparametric regression with fixed design, but then we'll have to deal with kind of discretization terms. So whereas here we can work directly with the L2 distance. So we have we just partition. We will take just regular histograms. So we partition our say the unit interval. So we have to build a prior on F. So we just take a step a histogram function with a random heights. Okay. So very simple. I take a regular histogram. So we can give ourselves a k, and I just split in k parts my unit interval. All right, and then I set the prior f will be given by the sum of hk. So hk are the heights indicator. So I call these intervals ik of ik. And how do I draw hk? So I will take, say, one distribution. I could take Gaussian. Let's take Laplace. It doesn't matter very much. If we have exponential tails here, it's a bit easier to verify this. Otherwise, you have to work a little bit more. So let's just take Laplace for simplicity. Okay, so Laplace double exponential. Okay, so density like this. So we have a base formula here in the white noise model. So to write it down, one has to be a bit careful with the dominating measure. So, but we can use Giesanov's formula or Cameron-Martin's formula here. That's the same. So let me just write it once. I will not use it. I just need to know that it exists so that I can check this theorem. But just to fix ideas, I'll just write it down once. So this I'll recall in the appendix of the notes. F over the integral of the same guy. Okay, so that's the posterior, and we, as I said a bit before today, the condition T here is satisfied in Gaussian white noise. It's very nice because everything is easy with the L2 distance. It's just a likelihood ratio test that you can take, and so it's also in the notes. It's just a few lines of proof, so you can check this easily. All right, so now a little theorem, more like a proposition, but let's, okay, so suppose that F naught belongs to a set of smooth densities. So, okay, so it will be the set of F's from 0, 1 to R that are C alpha, so that Hölder alpha for some alpha between 0 and 1. Okay, so Hölder alpha, C alpha is just the usual definition. Okay, So since alpha is smaller than 1, I don't have to take derivatives, so I just take this. And I assume also it's bounded by some m. Okay, so that I'll write in case one wants to write a uniform statement. So that's something I forgot to mention, is that as stated, so that it can stay within one board and that I don't have to use other parts. Well, here, these results actually, statistically, you want to make them uniform. So you don't, in statistics, we don't like pointwise result. We like to be able to compare, for instance, to minimax rate. We want to make this uniform. So typically here, you want to put a soup over theta naughts in a certain set. And so that's the set you would put here. So F alpha L, but not to surcharge the notation. I often, like sometimes on in the literature, I ignore the soup here. Okay, so suppose this F naught is alpha smooth. And so let pi be the random histogram prior. So the histogram prior, where I choose k to be equal to n over log n. So the log has no real importance. I could state it also without the log for the k, but then it would be another log factor in the rate. Then for c large enough, I have that EF naught. So now I switch to the F notation. Okay. I get this rate for the posterior c and log n over n to the power alpha over 2 alpha plus 1. So given x, so that goes to 1 as n goes to infinity. Okay, that's equivalent to larger and goes to 0. Okay, so that's a little result on histograms. Okay, so with this choice of k, you get that rate. Okay, so let's check this. So it's enough to check the conditions of the GGV theorem. Okay. So we'll just. So it's also to illustrate this. This approach is always so. Often, what happens is that in the prior mass condition. So to check it, we'll use some approximation term. So because our prior has a certain structure. Here it's some histograms. So first we'll say that histograms approximate well theta naught. Okay, so instead of theta naught, we'll take say a best histogram approximation of theta naught, and then I can compare this best approximation with the prior. Okay, so in a sense, I can project theta naught on histograms, and that's something that we'll do all the time, in that we use some approximation arguments from using the prior structure. Okay, so proof. So first, I'll just I mean, it's basic, but let's just do it slowly. Okay, so we have some the linear span of the indicators, and I'll project that the orthogonal projection of the function f. I'll write fk, and this is just the sum of the average values, right? So it's easy to check that you just get the average, okay, which is this. Okay, so that I denote by fk, and we have so the L2 norm of the histogram. Then so if I have of the kth projection is then just the same as 1 over k, the L2 norm of the sequence f bar, okay, in Rk. So I'll note this by okay. So norm k is just the norm, the Euclidean norm in R to the k. Okay. And last point is that if you have a C alpha L function, then you can approximate it by, so its projection onto histograms approximates it in some degree that depends on k, and that just, if you apply the mean value theorem, you just get that. The larger alpha, of course, the better the approximation in terms of the number of bins of the histogram. Okay, okay, so that's just a few basic facts. All right, so now let's verify the condition of the GGV entropy theorem. So as I said, the distance d, we can check that we can take the L2 distance here. So let's look at the prior mass. So something I didn't say either is that in the white noise model, another nice property is that actually the KL neighborhood is just the L2 neighborhood. So this is just, so that's another reason why it's nice, a nice illustrative example is that everything is really simple in terms of norms. So just the L2 ball for any epsilon, okay? So let's check the prior mass condition. So we have to check then that F minus F naught L2, this has sufficient mass. So as I said before, we'll just first project. So this is larger than F minus F naught k. So I project F naught onto histograms, smaller than epsilon n over 2. And not to have the over 2, I'll just write this, call this epsilon. And that's if, that holds if F naught by triangle inequality, it will hold if the projection is smaller than epsilon over 2. And this happens, this in terms happen, this is okay if L k to the minus alpha is smaller than epsilon over 2. Okay? So you get a condition saying that, so we'll get a few conditions on k and epsilon arising along the proof, and at the end we just verify that this guy and this guy verify the conditions in little waves here. Okay, so once we have, so this is now a histogram, so it's easy to compute the L2. The L2 norm is just I can translate it into the F bar case. So this is drawn from the prior now. So the heights of the prior are just the edge case. Okay. So I just need to look at what's the prior probability that HK, so that the sequence HK minus F naught bar k, so the average values of F naught in the k norm. So I said that the k norm is this divided by k. So I get, so what do I get here? So what I just want to say, so I don't even need to go to the k here. I'll just say that if all the heights are so if for all k I have that HK minus F naught bar k is smaller than epsilon, then we are fine, okay, because it just says that the histograms are close in sup norm, actually in max norm, by a little epsilon. So Okay, so then, so if we have this, then the L2 norm is, so I have a normalizing factor here, I think, that I'm forgetting probably, is the epsilon divided by k, probably, I guess. Okay, so if they are all bounded, okay, times k, then here with this normalization, I get that the L2 norm is bounded by epsilon. So we'll see that it doesn't matter here if I have some extra k. So, and here now, since I take an independent prior, this is just the product over k of the probability that, so this is a Laplace density, Laplace 1 minus f0 k bar smaller than epsilon times k. Okay? So here I'm just looking at, so since the function is bounded, I'm just looking at what is the mass that the Laplace density puts around some f naught bar k, which is in a compact interval. Okay? So I'm just looking at this mass here, and this is bounded from below by the width of the interval times the minimum of the density. But since the interval is bounded, the minimum of the Laplace density is also bounded. Okay, so this is bounded from below. So each one of these probabilities is just bounded from below by some d epsilon, some constant c epsilon k to the power, well, and then I take the product. But each of those is bounded by a constant times epsilon k. Okay, because of this little density element. Okay, and then I take the product, so I get k of them. So here what I get is that prior mass is bounded from below by c epsilon k to the k. Okay, so it's exponential minus k log 1 over c epsilon k. Okay. So I just need that k log 1 over c epsilon k is smaller than n Cn epsilon n squared. Okay, so that's another condition. All right, and then you have the sieve and the entropy. So the sieve is straightforward. So if we take like a sieve, the set of histograms such that the hk are all, say, in a set Hn, where this is just a set of sequences that are bounded by some, say, by n, k between 1 and capital K. Okay, then the prior mass of the complement is just by union bound, is just smaller than k times the probability that a Laplace Laplace 1 is larger than n. Okay, so that's smaller than k e to the minus n. Okay, so that's always smaller than exponential to the minus c plus 4 n epsilon n squared if k, say, is a little o of is a big O of n, say, which it will be eventually. Okay, and the entropy. So for the entropy, we just use that the L2 norm on histograms is up to a scaling factor, the L2 norm on Rk. And on Rk, we know how to compute entropies easily. Okay, so we just use that n epsilon Fn for the L2 norm is the same as, so I just have the scaling factor square root epsilon hn for the k norm on Rk. And then I can use that also hn is included in an L2 ball. So see if I want to go back just to the classical result on entropies of L2 balls. So if the L2 is bounded by k, sorry, if the maximum is bounded by n, then the L2 is bounded by square root k times n. Okay, so then I can replace this by this here. So I get E B Rk 0 square root kn for the k norm. And this is just the usual computation in Rk. So this is, so if this is smaller than constant times, so square root k n over square root k epsilon to the power k. Okay, so the entropy, so here there are little scaling factors, but if I have the unit ball, the entropy in terms of epsilon is epsilon to the minus k, so which I could recover here. So it's e to the k log c n over epsilon. Okay, and so that requires, so I need the last condition is that k log c n over epsilon is smaller than d n epsilon n bar squared. Okay, and if one puts all these conditions together, so I can just also take this to be epsilon and this to be k, and I can verify that these conditions are satisfied. Okay, so that's a first little proof for the histogram priors. Okay, so we get a rate that is nearly optimal. So it can be shown that for C alpha functions, the minimax rate of estimation is n, is this rate without the log. Okay, so there is just something that statistically is not super nice here. Yes.
So for this theorem holds for the L2 distance, right?
Yes.
Are there corresponding theorems for other distances, or it's
well, that's a good point. So we'll come back to that a bit later in the lecture. So here it turns out that for the histograms you could work on the fact that they are easy, the distances are kind of easily linked, but it's a general question to ask, and we'll try to come that a bit later. That's a good point. Yeah. Yes.
First, in the statement in your lecture notes, it starts with suppose linear for some alpha.
Yes.
And then a few lines later, then for any alpha.
Yeah, I think it's I corrected that. Yeah, yeah. So I've an updated version. I think this sounds familiar. That so what I meant is that here you can take any alpha in 0, 1 at the beginning, but there in this place, indeed, I think it's misleading. This so I have a new version. I'll send today. I'll try to send a new version of the notes because I've corrected a few typos.
Okay. Second question is just a notation question. I never remember what is this kind of equivalent symbol with the
this one.
Yeah.
It just means bounded from above and below up to universal constants C1 and C2.
It's a big theta.
Yes. Yeah. Sure. Okay. Exactly. Yeah.
A very last question. I'm sorry. So as I understand the prior for the histogram priors, we always have exactly the same Laplace law with the same decay rate, even when the number of intervals k becomes large.
Mm-hmm. Yes.
So this means that if you look at the integral of f, when k tends to infinity, you have a prior which somehow converges to saying that the integral of f is 0. Somehow the prior degenerates as k tends to infinity.
Sure, no. So, okay, true. In fact, here I just took Laplace just for simplicity, but you could also put some normalizations here, so you can check that if you take a Laplace with a certain scale, it will not modify too much the rate, because it will come up here, but and also here, but it will just put something depending on n here that will not the proof.
What I mean is that anyway, even if it seems as the prior seems to be more and more somehow.
Yes, no, that's a good point. Yeah.
We still have convergence for the Gaussian.
Sure. No. Yeah. Absolutely. Yeah. Good point.
My questions. Thank you.
Great. Other questions? Yes.
About the prior, you said the Laplace was not so specific, but it seems in the computations that if you take Gaussian priors, you won't get the same rate.
So you have to work a bit more. So here I took it for simplicity, because then you get exponential tails. So if you take a Gaussian, you'll get something. I think you get something similar. Because here you are bounded, so it doesn't matter much, and here you use a nice Gaussian tail bound. So if you would have some more heavier tails like Cauchy or something, you would need to work more to get this. So you would need to. So there are other versions of the theorem where you use different like local entropies, and you can. It's easier to verify, but I didn't want to go to these technical points here, so yeah. But it's not very important. Yeah. Thanks. Okay, so here maybe statistically the only thing is that actually I use. So you see, I use the parameter alpha in the prior. So this result is non-adaptive. Okay, so statistically we would not want to use. So if I use a different power here, I will not get this rate. I will get something that depends on what I put here. But we'll come back to that soon. Okay, so now we can move to Gaussian process priors. But at least I think it's good that we spend some time on an example where we can just come back to it to just recall in a setting where we can do easy computations what is the intuition of the conditions, okay, and that they can be checked. So one key idea is the fact that you use the structure of the prior here, the histogram, to approximate. First you project the theta naught onto histograms, and so you use this approximation result. Okay, so now we'll move to Gaussian process priors. So that's a very popular class of priors that is used a lot in applications. So in order to, so we call it GP, in order to verify these conditions, so we'll take a setting where we view the GP as random Gaussian elements. So in the supplement, in the appendix, I recall some facts about this perspective. So here I'll just recall the result that we need. So we'll view the Gaussian priors as random elements in some Banach space. So the Banach space, there will be only two cases that we consider. L2 equipped with this L2 norm and C0. So I think there is a typo somewhere in the notes, I think at the beginning, where I put L infinity, but it should be C0. Okay, so sorry about that. Equipped with the L infinity norm. Okay? And so let's start with maybe the most famous example. So as I recalled already yesterday, so Brownian motion you can view as either in L2 or in C0. KST equals S inf t. Okay, so it's a half smooth, we said. Then we have, so for this lecture and for tomorrow, it will be important to have this Gaussian series prior, or more generally the series prior, but here we'll take Gaussian coefficients. So I take this j minus alpha, minus a half minus alpha, sorry, zeta j, ej for some basis, orthonormal basis of L2, and zeta j, I take n01 AIB. Okay, so two examples to have in mind. So the theory for those GPs, what's very nice with Gaussian processes is that they are somehow, we can understand their properties based on a space which is the reproducing current Hilbert space, H. So I recall the definition. I don't have time really to go through here, but just give me the intuition of what the RKHS here is. So just give two examples. So if you have a Gaussian vector, so just a process, a discrete process on just a finite number of coordinates. So suppose I have a vector of dimension d that is distributed as a Gaussian, so n0 sigma, that's a Gaussian vector. So the RKHS in this case, so in this case 1, then H is just RD, but with a modified norm. With the norm, or let me give the unit ball, H1, okay, is an ellipsoid. So, and the ellipsoid is defined by the inverse of sigma. So here I assume that sigma is positive, so that I can have an inverse. So x transpose sigma minus 1 x is smaller than 1. So H1 here is, so this is actually the norm RKHS squared, and this is the unit ball. You can, it's not difficult to show this. So what you have is that it's kind of, it twists the inner product, and it kind of, so if sigma is diagonal with decreasing coefficients, what you get is so sigma 1 squared or arbitrary coefficient sigma I that are positive. Then here what you get is sum over k from 1 to d of sigma k minus 2 xk squared smaller than 1. Okay, so it's an ellipsoid that gets kind of shrinked if sigma k go to 0. Okay, and more generally, you can show that for the, so this series prior is actually a sort of infinite dimensional analog of this, where you take the dimension to infinity, and indeed you can show that then in this case the RKHS is a Sobolev type space, and the norm is just a Sobolev norm. Okay, so the intuition, even if you don't know the RKHS, doesn't matter too much. I'll recall the properties, but the intuition that you can keep is that it's a set, it's a Hilbert space with a norm that gives some smoother objects than the prior itself, say. Okay, so what is the, so if I call this prior a star, so that's the second example. So for the GP, for the series prior star, the RKHS is the set of functions f, which have coefficients fk in the basis, k, in the basis such that k, 1 plus, here I put k, but it could be j as well. Okay, so it's a Sobolev type space. And the unit ball is just a Sobolev type ball. Right? So now we come to an important definition, something that will arise in the determining the rate for the GPs. So suppose we have a GPW in B separable Banach space with RKHS H. And suppose that we have a function W that is in the closure of H in B. Okay. Then we set phi W epsilon. So this is something that you can check. So for many Gaussian processes, we know how to characterize the RKHS. So we know whether then we can check just by approximation properties what if a function belongs to the closure. We'll see with an example, for instance, with Brownian motion. So we have something that's called the concentration function of the GP. And it has two parts. It has a part that consists of an approximation term over 2, and a part that is what's called the small ball probability. Okay, so that's a definition, and it will it's important for the rates. So there are two parts. So the first part is, so if it happens that W is in the RKHS, then the first term, so this is an approximation term. So if by chance W is in the RKHS, then this term is actually constant, because you can just take H equal to W, and this norm is constant. Okay, and this is something that's a small ball term. Okay, so for Brownian motion, for instance, it would if you are in the case with the infinity norm, you are asking what is the probability that it stays within a tube. Okay, with say in 0, 1, that it stays between 0 and so in absolute value smaller than epsilon. Okay, so it's something very small of very small probability, but you can quantify it. Okay, so for instance, for Brownian motion, so you can. So this term is also written phi 0. Okay, because if you take W equal to 0, you can take H to 0, and this term vanishes. So it's also phi 0 of epsilon. And so for Brownian motion, one can show that phi naught of epsilon for both the L2 and in the L infinity norm is of the order epsilon minus 2 for both the L2 and L infinity. Okay, so just a little example. And for the approximation term, if W is not in the RKHS, you pay something, and you pay by, so what is the best approximation of W at epsilon distance in B by elements of the RKHS, and you pay this, so this norm will grow because W is not in the RKHS, so this will blow up to infinity as epsilon go to 0. And so you have to balance these two terms. Okay? So for now, it's just a definition. But in a second, we'll see that this actually determines at least an upper bound for the rate in the GGV theorem. Okay, so let me recall just a few properties, a few classical properties of Gaussian processes. So I don't really have time to go, so I'll try it in the appendix of the notes to make a little survey on these properties, mostly without proofs. But so we'll need a few properties. So the classical property is that if H is in the RKHS, you can shift actually so you have a formula called Cameron-Martin formula, and you have that that the measure induced by W plus H is absolutely continuous to the original distribution of W itself. You have, for us, maybe one of the most important properties is that, so thanks to this change of measure formula, which, I mean, I've written it in the notes, but so here I'll just state the property that we need. I'll come back to it a bit later in the lectures. An important property is that if you look at the probability that the mass of a ball in B, so what is the probability that the Gaussian process is around a certain function W naught? So assuming that W naught is in H bar of B, so this you can bound by the small ball probability, by the concentration function from below. Okay, minus phi W naught of epsilon if W naught belongs to H bar of B. Okay, and the idea is actually to use this change of measure formula here. So of course, in general, you cannot use it because W is not in H, but it doesn't matter. You just take an approximating sequence. And actually, this is implied by something we'll use in a moment, by the fact that if you have an element in the RKHS, then it's easier to bound from below this probability. So this probability around a certain element of the RKHS is larger than, so a bit from the change of measure formula, so the minus h squared over 2. So that's familiar from the Cameron-Martin formula, for those who know this. And for those of you who know it, and then this is the small ball probability. Okay, so if you combine this with this definition, you can get this. Okay, and the last point is a concentration inequality that you can guess we'll use here, which is Borel's inequality. So it's a famous concentration inequality, which says that the probability that W is not in epsilon, so here I use 1, so B1 means the unit ball of B, and H1, as I mentioned already, means the unit ball of the RKHS. So the probability that W doesn't belong to epsilon B1 plus M H1 is smaller. You can bound in terms of the distribution function. So capital phi of U is just the usual, the probability that N01 is smaller than U. Okay. Okay, so it's phi minus 1 e to the minus phi naught epsilon plus m. Sorry. Okay, so you can control in terms of epsilon and m. Okay, and so now with these tools in hand, we can prove the following theorem, which is a sort of pre-rate theorem, a pre-concentration theorem that has the purpose of verifying this for Gaussian processes. Okay. So you have the following theorem. So 2.3. So we take a GPW with RKHS H in B. And we take W naught, here, this little technical condition. Suppose W naught is such that the concentration function of the GP at the W evaluated at epsilon n is smaller than n epsilon n squared. So we have this equation, sort of, or inequation to solve. Then for C larger than 1 with C n epsilon squared larger than log 2, that's not very important, so there exist sets Bn included in B such that we have something which very much looks like what's on the board over there. So the entropy of these sets in B is bounded by 6Cn epsilon squared. The prior mass of the complement of Bn is exponentially small. And finally, the prior mass condition is verified. For so the prior mass not in the KL neighborhood, but in the, so that's why I call it a pre-concentration result, because sometimes we may have to work still a little bit to apply it to a real statistical model, because we still have to link distances. Okay, so here the only thing that we will miss to apply this, so that you need to add, is just a statistical model which will give you a distance d, and then which will also give you a certain Kullback-Leibler ball. But if you are able to relate this ball, if this ball contains, say, a B ball, then you can use this result to verify these conditions. Okay? So let's prove this. So 3 is actually straightforward given the properties on the right-hand side from this one here. Okay, this square. Okay, because you bound this from below by this, and then you know by assumption that the concentration function is bounded from above by n epsilon n squared. So then this is bounded from below with the minus by what you want. Okay, and 2 is also quite immediate from these properties of GPs. We can just set Bn. So from the Borel inequality, it suggests that we set Bn equals to epsilon B1 plus, so let's take a certain Mn that we'll calibrate in a second, H1, okay, for epsilon n and Mn to be chosen. And then by Borel's inequality, the probability that W is not in Bn, this is smaller than this function over there. So this phi bar, okay, so 1 minus phi of phi minus 1 of e to the minus phi 0 of epsilon n plus mn. Okay, and now we just check that if we choose mn wisely, we will have inequality 2. Okay. So let me erase here. Okay, so let's now just take, so we know that e to the minus phi naught of epsilon n is larger than e to the minus n epsilon squared, and is larger than, so if I take c larger than 1, is larger than this. Okay, so that implies that since phi minus 1 is increasing, phi minus 1 of e minus phi naught of epsilon n is larger than phi minus 1 of e to the minus cn epsilon n squared. And I'll take this to be so this will be, I define as minus mn over 2. Okay, and then the probability here, so say star. So I hope there is not another star in the board. No, I think I've erased those. Star is then bounded from above by phi. So sorry, 1 minus phi. So we get this. So here mn is, so this is, I can use this. So this larger than this is minus mn over 2. So I get here mn over 2. Okay, and this is equal to e to the minus c n epsilon n squared, just by using the symmetry of phi. Okay, so the last condition we need to check is now the entropy condition, and I think we'll probably finish there for today. After the theorem, I'll just say a few quick comments. So let's finish the proof for this. So let's take H1, Hn. So we want to check this entropy condition. So we want to cover this sets Bn here by balls in B. Okay. So I'll take some points in Mn H1, and at the end I will just add epsilon n B1. So suppose I have point in Mn H1, a maximal set of points, separated by at least 2 epsilon n in B. Okay? So if I have a 2 epsilon n separated set of points, it means that if I take epsilon n balls around those, so I shouldn't erase, I think this, I'll keep. So it means that so if I have a separated set of points by at least 2 epsilon n, it means that if I take balls of radius epsilon n around those, they don't intersect. Okay, so it means that H1 plus epsilon n B1, B1 is the ball, so epsilon n B1 is just a ball of radius epsilon n, etc. Epsilon capital N. So we'll see that capital N is finite during the argument. So Hn epsilon n B1. So those are balls which are disjoint. So in particular, this implies that 1 is larger than the probability that W belongs to one of these balls. So from 1 to n of Hj plus epsilon n B1. Okay. And since they are disjoint, this is just the sum of the probabilities, that W belongs to Hj plus epsilon n B1. Okay, so here you see that this is nice because it's exactly something which is the line below actually, which tells you what is the probability that W minus Hj in the B norm is smaller than epsilon n. This is lower bounded by this quantity. Okay, so if you put this together, you get that this is larger than the sum for j equals 1 to n of e to the minus. So here I use what's here below, squared over 2, and the small ball term, which is actually e to the minus phi naught of epsilon n. Okay, and so since all the Hj's, they are in Mn H1, so this is larger than n times, so every one of them is bounded by Mn times, the square norm here is bounded by Mn squared, Okay, so it's lower bounded by minus mn squared over 2 minus phi naught of epsilon n. Okay, and so now we can use the definition. So by definition of mn, okay, which is minus 2 phi minus 1 e to the minus cn epsilon n squared. So you can use here just the classical inequality on phi minus 1. So that's about Gaussians, everything is known. Well, more or less. So you have some classical inequalities just to bound this. Essentially, the way you can view this is just that you invert the e to the minus x squared over 2 function, right? So it's normal to have square root log something that appears. 1 over y for y, so that's the precise inequality with constants, but we don't care too much about the constants here. So using this, you get that mn is smaller than 2 square root 5 over 2 cn epsilon n squared. Okay, so if you put everything together, you get that n is smaller than exponential. So mn squared. So I pull it on the other side, square of this. So I get divided by 2. So I get 5 cn epsilon n squared plus. And now phi naught of epsilon n, of course, is smaller because it's a part of the concentration function is the small ball probability term. Okay, so this is smaller, so I just get extra an n epsilon n squared. So this is, as announced, smaller than what we have over there. Okay, and so we are nearly done. Now we just need to show that this is bounded from above by n. Okay, so in order to do that, that's kind of very kind of classical now, because we have a set of separated points, so we know that this will bound from above the entropy of mn h1 for the B norm. I claim that this is bounded by n. And why? Because if you just take now the same set of points here, but with the balls of radius 2 epsilons, so they don't touch because they are separated by at least 2 epsilon n. No, sorry, they will touch, but you don't miss any point. Okay, so if you take balls of radius 2 epsilon n now, you cannot miss a point, because if you would miss a point, then descent wouldn't be maximal. You could add it. If you miss a point by these balls of radius 2 epsilon, it means that there exists a point which is separated from all the other ones in this maximal set by at least more than 2 epsilons, which contradicts the maximality. Okay, so that shows this, and then we just use the fact that if you add epsilon n on both, if I just add an epsilon n b1 here, I just add an extra epsilon n to the left, b, and then so this is smaller than this, which is in turn is smaller than n. Okay, because if I get a covering here, it induces a covering also here. All right, and so that concludes the proof. All right, and so now the only thing that is left to understand the rate of the posterior convergence rate for the Gaussian process is to solve this equation. Okay, and let me just comment on that before I take questions. Is just then you need to understand the approximation term, which you'll know how to handle or to bound as soon as you know the RKHS, okay, because it's in terms of the approximation by elements of the RKHS. And the small ball probability, many of those are known for GPs in the literature, and there are general tools to bound those by actually using the entropy. So the entropy of the unit ball of the RKHS will give you a way to control the small ball probability. So I'll give one or two examples tomorrow about this. But essentially, this gives a principled way to give you, okay, you have a Gaussian process and a square exponential, okay. This will give you the rate if you solve this equation. Okay, thank you very much.